Welcome everyone to Cognitive Spirals. Today, we're diving deep into the fascinating world of AI, specifically looking at the concept of unsupervised elicitation of language models. It's a mouthful, I know, but the implications are huge.
Absolutely. It's about teaching these models to learn and refine their understanding of language without constant human intervention, right?
That's the theory, but I'm always a little skeptical of the unsupervised label. There's always some kind of bias or human design constraint baked in, even if it's subtle. Isn't it really more or less supervised?
I think that's a fair point. And it leads me to wonder, what are we truly hoping to elicit? Are we just looking for better pattern matching, or are we hoping to stumble upon some fundamental principle of language?
Those are excellent questions. The core idea, as I understand it, is to let the language model learn from the vast amounts of unlabeled text data available. The hope is that through this self-tuning process, the model will discover hidden structures and patterns, mirroring how the human brain learns language naturally. Think about how a child learns to speak. They're not explicitly taught every rule. They pick it up through exposure.
Exactly. And with the sheer scale of data we can throw at these models now, it feels like we're approaching a tipping point. The complexity of these models, combined with massive data sets, could lead to emergent capabilities we haven't even predicted yet.
Emergent capabilities is the magic word everyone loves to throw around. But what does that really mean? A really good autocomplete? A convincing chatbot? I'm not convinced that's the same as genuine understanding or intelligence.
I'm with Sarah on this one. It feels a bit like brute force. We're hoping that enough data will somehow compensate for a lack of a truly intelligent algorithm. What about the spatiotemporal aspect? Language isn't just a sequence of words, it's embedded in a context, a time and place. How are these models capturing that?
Well, transformer networks, which are the backbone of most of these language models, do have mechanisms for attending to different parts of the input sequence. That allows them to capture some contextual information, right? It's not perfect, but it's a start.
Yes, and the self-attention mechanism in transformers is designed to weigh the importance of different words in the input sequence, allowing the model to understand relationships and dependencies. Think of it like this. If you're reading a sentence, you're not just processing each word in isolation, you're constantly relating it to the words that came before and after. Self-attention tries to mimic that.
Exactly. And the more layers you add to the network, the more complex these relationships can become. It's like building a hierarchical understanding of the text.
But it's still just pattern recognition, isn't it? It's not reasoning. It's not understanding the meaning behind the words. A language model can generate a grammatically correct sentence about, say, the consequences of climate change, but does it actually understand the science? Does it understand the ethical implications? I doubt it.
That's where the translation between different coordinate systems comes in, I think. If a model could take that language-based representation of climate change and translate it into a spatiotemporal model showing the predicted impact on sea levels, that would be something entirely different. It wouldn't just be spitting back information, it would be demonstrating understanding.
Okay, but even if it's just pattern recognition, the patterns are incredibly complex. And with self-fine-tuning, the model is constantly refining its understanding of those patterns. How does that compare in terms of computational cost and efficiency to more supervised methods? If it scales well, it could be a game changer.
That's a great point. Think about how much effort goes into labeling data for supervised learning. It's incredibly time consuming and expensive. If we can get comparable results with unsupervised methods, that's a huge win. And the self-tuning aspect is really fascinating to me because it mirrors the constant refinement that occurs in the human brain through experience. It's like the model is constantly pruning and strengthening connections based on its interactions with the data.
And that's where I think we're seeing the potential for AGI. These models are becoming more adaptive and evolving. They're not just reactive, they're actively learning and improving. It's a dynamic plasticity that's really exciting.
I think you're jumping the gun a bit. Adaptive, yes. Intelligent, I'm not so sure. It's still fundamentally a statistical model. It's predicting the next word in a sequence based on probabilities. That's not the same as having a conceptual understanding of the world.
Exactly. Think about driving a car. You're not just predicting the next movement of the steering wheel, you're constantly updating your internal model of the car, the road, the other cars around you. You're translating between visual information, spatial awareness, and motor control. Current language models can't do anything like that.
But isn't there potential for bridging that gap? If we can understand how the brain represents space and time, how it integrates different sensory modalities, could we potentially translate those principles into AI architectures? I'm thinking about the hippocampus, for example, and its role in spatial memory. Could we build AI systems that use similar mechanisms to represent and manipulate spatial information?
Maybe, but wouldn't it be more efficient to focus on optimizing the existing architectures? We know that scaling up these models works to some extent. Why not focus on that, and then later try to incorporate biological insights?
Because just scaling up the existing architectures is like building a bigger and bigger house on a shaky foundation. We need to fundamentally rethink the way we're representing knowledge. Neuro-symbolic approaches, for example, offer a way to combine the strengths of neural networks with the rigor and explainability of symbolic reasoning.
That's where I think the key might lie, finding a way to translate between those different representations. Think of it like this. You have a pixel-based image, and you want to describe it in language. That requires a translation from one coordinate system to another. If we can find a general algorithm for that, we might unlock a whole new level of intelligence.
So, Sarah, when you talk about neuro-symbolic approaches, what specifically do you have in mind? Are there any examples that are particularly promising?
There are a few. Some approaches involve using neural networks to learn symbolic rules from data. Others use symbolic reasoning to guide the training of neural networks. For example, you might use a symbolic planner to generate a sequence of actions and then train a neural network to execute those actions. The problem is that most of the research is theoretical or small scale. We need to see more real-world applications.
But aren't those approaches inherently limited by the expressiveness of the symbolic language? How do you represent things that are fuzzy or uncertain? Neural networks are much better at handling that kind of ambiguity.
That's where I think the spatiotemporal aspect comes in again. Uncertainty can often be represented as a probability distribution over possible states in space and time. If we can build models that can reason about those distributions, we can handle ambiguity more effectively.
And that reminds me of the concept of distributed representations in the brain. Information isn't stored in a single location. It's spread across a network of neurons. Maybe we can translate that idea into AI architectures, allowing them to better handle the contextual nuances of language.
Okay, but how do you even evaluate progress in that direction? Current metrics are so focused on task completion. How do you measure understanding or reasoning ability? We need more sophisticated evaluation metrics that capture the nuances of emergent capabilities.
I agree. And we need metrics that go beyond just performance. We need to be able to understand why a model is making a particular decision. We need explainability and transparency.
Exactly. If we can't understand how a model is reasoning, we can't trust it. And that's especially important in high-stakes applications like healthcare or finance.
So thinking about future research directions, what would each of you like to see explored further based on your different perspectives?
I'd like to see more research on scaling up self-supervised learning methods. How can we make these models even bigger and more complex? And how can we accelerate the self-tuning process to converge more quickly on desired language capabilities? We need to find better ways to leverage the vast amounts of text data available.
I want to see more research on neuro-symbolic architectures. We need to explore how to combine the strengths of neural networks with the rigor and explainability of symbolic reasoning. And we need to see more real-world applications of these approaches.
I'd like to see more research on spatiotemporal reasoning. We need to develop algorithms that can represent and reason about time and space in a more sophisticated way. And I think the key might be finding a way to translate between different coordinate systems.
From my perspective, I'm particularly interested in exploring how insights from neuroscience can inform the design of AI architectures. How can we translate the brain's intricate structure and function into computational models? And how can we leverage concepts like distributed representations and brain plasticity to create more adaptable and robust AI systems?
One specific question I have. What specific architectures or variations of transformer networks are proving most effective in the unsupervised elicitation process? Understanding the underlying mathematical formulation of these models will give us valuable insight into the algorithms themselves.
I'm really interested in how biological brains encode information. It's fascinating how interconnected and hierarchical their representations are compared to the relatively flat, amorphous representations of current LLMs. I wonder if there's a way to translate those biological constraints into computational algorithms.
I need to explore how different coordinate systems, Cartesian, polar, etc., are used in various fields: physics, geometry, even in different programming languages, and how a hypothetical algorithm might translate between them. This could be a crucial piece for adaptability, allowing the model to switch between descriptions of the same entity.
And I think we should really focus on how we can map the neural processes involved in language comprehension and production onto computational models. Current language models are black boxes in many ways. How can we use neuroscience to make them more interpretable?
It's true, it's hard to tell why they are making certain decisions, but honestly, that's kind of how the brain works too. We often don't know why we make a snap decision.
But at least we can introspect and try to figure it out. These models can't even do that.
Exactly. And that introspection, that ability to reflect on our own thought processes, is crucial for learning and adaptation.
Okay, but back to future research. Another area I find fascinating is the idea of self-tuning in language models. It reminds me of the constant refinement that occurs in the human brain through experience and learning. If we can replicate this dynamic plasticity in AI, perhaps we can unlock a new level of intelligence, one that isn't just reactive but truly adaptive and evolving.
That dynamic plasticity is exciting, but it still needs to be efficient. How does the self-fine-tuning process compare in terms of computational cost to more supervised methods? We need to be realistic about what's actually feasible.
And we need to be careful about what we're optimizing for. Are we just trying to create models that are good at generating text, or are we trying to create models that actually understand the world?
Yes, because if we're just optimizing for text generation, we might end up with models that are incredibly fluent but also incredibly wrong.
That's a really important point. And it brings us back to the importance of grounding language in the real world. We need to find ways to connect these models to sensory data, to physical experiences, to the spatiotemporal context in which language is used.
Okay, but how do you even do that? It's not like you can just plug a language model into a robot and expect it to learn everything on its own. There's a huge amount of engineering involved in building robots that can interact with the world in a meaningful way.
That's where I think neuro-symbolic approaches can really shine. You can use symbolic reasoning to guide the robot's actions and then use neural networks to learn from its experiences.
And the robot could be constantly translating between different coordinate systems, from the visual input to the motor commands to the language-based description of its actions.
And the language model could be constantly learning from the robot's experiences, refining its understanding of the world and becoming more intelligent over time.
It sounds great in theory, but it's a long way from being a reality. We still have so many challenges to overcome.
But it's a challenge worth pursuing, I think. Because if we can crack this nut, we might be able to create truly intelligent machines that can help us solve some of the world's most pressing problems.
Absolutely. And the potential benefits are enormous.
Well, this has been a fascinating discussion. It's clear that there's no easy answer to the question of how to build more intelligent machines. But by combining insights from neuroscience, AI, and other fields, we can make progress towards that goal. Thanks to you all for your perspectives.
Thanks for having me. It's always great to debate these topics.
My pleasure. Always happy to share my skepticism.
Thanks. It's been thought-provoking.
And thank you to our listeners for joining us on Cognitive Spirals. We'll be back next week with another deep dive into the world of consciousness, cognition, and machine intelligence.
Before we completely wrap, I was wondering, is there any evaluation metric for language model performance that captures the nuances of emergent capabilities, particularly in the context of self-fine-tuning? The current metrics seem quite limited.
Exactly. I think it goes hand in hand with the explainability issue. You can't really evaluate emergent capabilities without understanding what they are.
Maybe something that assesses the model's ability to generalize to new, unseen situations, or its ability to reason about counterfactual scenarios.
I like the idea of counterfactual reasoning. It gets at the model's understanding of cause and effect. Maybe we can develop metrics that specifically test for that.
Or perhaps metrics that measure the model's ability to learn new concepts from a small number of examples, like humans do. That would be a sign of true intelligence.
And we need to be careful not to just optimize for these new metrics. We need to make sure that we're actually measuring what we think we're measuring.
It's a tricky problem, but it's a crucial one. Because if we can't accurately evaluate progress, we're just flying blind.
Agreed. It needs further evaluation, but this is a good place to wrap up. Thanks, everyone. This was great.
Thanks.
Bye.
Goodbye.